All right, in this lesson, we are going to be looking at series, convergence, and divergence. We're going to look at several different tests, ways that we can determine if a given series either converges or does not, diverges. We're going to be building on our last topic, which was looking at seeing whether the terms in a sequence converge or diverge. All right, so let's get started. So a series is the sum of the terms in a sequence. All right, so just adding them up. Finite sequences in series have defined first and last terms, whereas infinite sequences in series continue indefinitely. Informally, a series is the result of adding any number of terms from a sequence together. See, we've got our list view here. We've got the first term, a sub 1, plus the second term, a sub 2, plus, and so on. All right, a series can be written more succinctly by using the summation symbol. So let's look at a couple of these different versions. All right, so for for a given sequence, in blue, we've got 5, 10, 15, 20, and so on. If we were to rewrite that as an infinite series, all right, notice the 3 dots and notate that it's going on forever. We're just going to add those terms, 5 plus 10 plus 15 plus 20, and so on. Okay, more likely, you'll see it written in summation notation, all right, to where we have a rule for that sequence. All right, we've got that that 5n there, and we've got that sigma. Again, that represents summing up our terms. Underneath the sigma, we've got n equals 1, which is kind of our starting point, and on top we've got our ending point, all right, which term number to stop at. If we're doing an infinite series, which is what we're going to be focusing on, there's going to be an infinity on the top. All right. For infinite series, we can look at the sequence of partial sums. That is looking to see what the sums are doing as we add additional terms. In general, the nth partial sum is a series is denoted as S sub n. This can be explored on a calculator by adding sequential terms to the aggregate sum. All right, so before we get to our calculator, let's look at example number 1. It says for both a sub n equals 1 over n and b sub n equals 1 over n squared, generates a sequence of partial sums s sub 1, s sub 2, and so on. For each, then determine if the series converges or diverges. Okay, so let's look at this first one. So let's look at a sub n. If we're looking at that series, then in summation notation, we're just looking at sigma from n equals 1 to infinity of our function 1 over n. All right, and again, our goal is to determine whether this series, whether the sum of this sequence converges, approaches a certain value, or it doesn't, it diverges. All right, so the way that we're going to start off doing this is to kind of get an intuition of these series is looking at partial sums. All right, so if we look at, let's say, S sub 1. Again, that's the sum of just the first term. All right, well, if we plug in a 1, 1 over 1 is just 1, so that's 1. All right, if we look at the sum of our first 2 terms, all right, S sub 2. Well, that's 1 over 1, so 1 over 1 plus, and then the second term is going to be plugging in a 2, 1 over 2, 1 and 1/2 is just 1.5, or 1.5. All right, so we could continue to do that on and on. And if we did that, we could look at bigger and bigger values of n. So adding in more and more of those terms. And we would want to go out far enough to where we got a decent idea of what our sequence is doing. This is awesome. Hello. Okay, so we've got the sum of the first 10 terms goes to 2.929. Sum of the first 100 goes to 5.187. First 1,000 and the first million terms. So we can see those values continue to increase. Even though they're not increasing rapidly, they are increasing. It doesn't look like they're approaching a certain value. I mean, we went out 1 million terms, and it's still getting bigger and bigger. So we can say that for all intents and purposes, this series diverges. All right, one of our tests later is going to show that in a different way, that it does indeed diverge. All right, on your own, in your notes, do the same thing. Look at the first several partial sums and then go out to large numbers like 1,000, 10,000, a million, and whatnot for this second function here, b sub n, which is 1 over n squared, and determine whether it converges or diverges in your notes. Okay, looking at example 2. It says, given this series, 3 over 2 to the n from 1 to infinity, and it gives us both the sigma notation and the list form there. It says find the first 10 terms of the sequence of partial sums and list below. Based on this sequence of partial sums, do you think the series converges or diverges, and to what? All right, and it gives us a hint there. Okay, so first thing, it says, looking at the hint, first rewrite the rule of the sequence so that it looks like an exponential function of n. All right, so exponential function. So that was our geometric sequences that we touched on in the last topic. So if we're going to rewrite this, then let's see, 3 over 2 to the n. We can rewrite that as 3 times 1 over 2 to the n. All right, the 3 is not being raised to the n power, so we need to pull that out before we put that nth power up there. Okay, so now we've got an exponential there. We've got 1/2, which is what is being raised to the n power. That's our common ratio, essentially. Looking at the first 10 terms. So if we look at just the first term or two, all right, so if we look at the first term, we plug in a 1, we get 3 times 1/2, that's 3/2. We look at the second partial sum, which is the sum of the first 2 terms, so we need to plug in 2, so we get 3 times 1/2 squared, which is 1/4, so that would be 3/4. So 3/2 plus 3/4. All right, and that would give us 2 2/4. And we could keep going, but that's going to get kind of tedious. So let's look at how we can do this in our calculator. All right, so in your calculator, we're going to use a function called cumulative sum, which is kind of the calculator's way of doing a partial sum. And then we're also going to use the sequence function. Okay, so here's the button presses we're going to do. We're going to go into our list menu, and we're going to choose option 6 for cumulative sum. And then we're going to go into our list menu again and choose option 5 for sequence. All right, so second list, go over to the ops menu. Option 6 is that cumulative sum. And then we want to sum up our sequence. So going back into our list menu, go over to our ops, and then option 5 is our sequence. And this brings up, if you're on the 84, this brings up a little menu we can plug in these same values in. Plug in these values for our rule specifically. So our expression, all right, so that first argument, they want us to put in the rule. So the rule of our sequence is 3. times 1/2 to the n power. All right, and if you're in sequence mode in your calculator, that variable button will come up as n. If you're in function mode, it doesn't matter, x or n, as long as in this next part we put in that same variable there. All right, you could put in that initial function too. It doesn't matter, same thing. All right, so start. So this is our start value here. That's our 1, and we're going up to. It would be nice if there was an infinity button, but on our 84s there's not. And so looking at our problem, we want to go to the first 10 terms. So we're going to look at our first 10 partial sums. All right, and the nice thing about our calculator is it's going to give us all 10. It's not just going to give us S sub 10. It's going to give us all of them in a list. All right, we're going to step by ones. We don't want any decimal values in a sequence. And then we're going to paste that in. And if you're on an 83, this is kind of the way that you would want to type it in after you do the cumulative sum in sequence with the commas in there. And then press enter. And notice how it gives us this array, this list of values that starts with a squiggly brackets on the left. And that first value, 1.5, lines up with what we got for our 3/2 for our first term. All right, the second one lines up with our 2.25. All right, and then the third one, the fourth one, and then it kind of cuts it off. But as long as you haven't typed anything else in, if you press cursor to the right, then it's going to kind of slide over one digit at a time until you get to, it'll stop at the last one. All right, so that 2.997 is the sum of the first 10, and all those in between are those other values. Okay, so looking at our first 10, let's see if I can make that a little bit bigger. There's our first 10 partial sums. Again, those are summing up that n number of terms each time. All right, so looking at that list, that's different than the last example we were looking at. That definitely looks like it's approaching 3. All right, so the sum as we go out 10 terms looks like it's approaching 3. So that's going to be our well, that's really all they ask, is to look at the first 10 partial sums. All right, cool. Example 3, I want you to try that on your own. Use your calculator to find the first 5 terms of the sequence of partial sums, and then use that to determine whether you think the series converges or diverges. So ours, in example 2, look like it converges to 3. All right, try example 3 and see if you get a convergent or a divergent series. All right, we're now going to look at several families of infinite series and several tests that will help us determine whether they converge or diverge. For some that converge, we might be able to give the actual sum or an interval in which we know the sum will be. For others, simply knowing that they converge will have to suffice. All right, our first test that we're looking at is called the geometric series test, or the GST. Okay, geometric series is in the form sigma notation, all right, of n equals 0 to infinity of a times r to the n, or from 1 to infinity of a times r to the n minus 1, where a doesn't equal 0. All right, the geometric series diverges if the absolute value of r is greater than or equal to 1. And if the absolute value of r is less than 1, then the series converges to the sum s equals a sub 1 over 1 minus r. Right? That a sub 1 is just that initial term. In the sequence, right? Where a sub 1 is the first term, regardless of where n starts, and r is the common ratio. All right, so notice it says regardless of where n starts. This kind of hints at the fact that This can be applied to sigmas other than just where our n value starts at 0 and 1. As long as we use that a sub 1 to mean that initial term, we can apply this GST. All right, so let's look at some examples. Example 4 says, using the GST, determine whether each series converges or diverges, and if it does converge, find the sum. All right, so in part A, we've got the series from 1 to infinity of 3 over 2 to the n. All right, that should look familiar. That is what we were just looking at on the first page. So let's rewrite that. All right, I think we're actually done with our calculator for now, so I'm going to get rid of that. All right, we rewrote this as 3 times 1/2 to the n. All right, that kind of reveals it as a exponential or a geometric exponential function or a geometric sequence. All right, so that shows our r value there is 1/2. And that means that absolute value of 1/2 is less than 1. All right, that points us to a convergent series. So we can say converges by GST. And then the directions said if it converges, and find where it converges to. So let's do that. So our sum equals our initial value. So if we plug in that 1 there, then we're just going to get 3/2 divided by 1 minus r. So 1 minus 1/2. All right, so what do we got? 3/2, keep, change, flip. Oops, that's not a half. 2 over 1. All right, so that gives me 3 over 1, which is just 3. And that lines up with what we found on previously, right? Let's double check that. Yeah, so this same series there, we found through partial sums that it looked like it converges to 3. So here's a test that shows that for certain that is the case. All right, let's look at example B. Example B, we've got 3/2 to the n. Notice how this is different than the last one. The 3 is being raised to the n power. All right, still geometric. One thing I like to do is when you recognize that it's geometric, then I kind of go ahead and jot that down, and then I'll put whether it converges or diverges above it. It's just something I use to remind myself to include that, because when we're asked to find whether a series converges or diverges, we want to make sure we jot down which test we used. All right, so my r value is 3/2. The absolute value of 3/2 is greater than or equal to 1. All right, and that tells us that it diverges. Anytime that r value is bigger than 1, think about that as an exponential function that is growth as opposed to decay, so it's going to diverge. All right, one more example. In part C, we've got 3 times negative 1/2 to the n. Looking at this series, notice this one is going from 2 to infinity. We can still use the GST for this one. So I'm going to go ahead and say, all right, so by GST. And then let's look at our r value. So our r value is our first negative r value, and that's okay. R value is negative 1/2. Absolute value of negative 1/2 is just 1/2, and that's less than 1. All right, that means that it converges. All right, so it converges by GST. We want to find the sum. So our sum is going to be our initial value. All right, so be careful. Our initial value here, we're going to plug in 2 into n, not 1 or not 0. All right, so for our initial value, that's really a sub 2. We've got 3 times negative 1/2 to the second power. All right, so that's going to be 3 times negative 1/2 squared, which is 1/4. So that's going to give us 3/4 that goes on top, and then 1 minus, we want to go back to our original R value there, so negative 1/2. Okay, so our sum is 3/4. Keep change flip. That's going to be plus positive. So 1 and 1/2 is 3/2. Keep change flip. It's going to be 2/3. We've got 3 on top, 3 on the bottom, and then 2/4 simplifies to 1/2. All right, so that's our sum. Whoa, yeah, puppy. So it converges by GST to 1/2. Okay, next test is our nth term test for divergence. All right, it says if the limit as n approaches infinity of a sub n does not equal 0, then the series of a sub n from 1 to infinity diverges. All right, note this does not say the converse, that if the limit as n approaches infinity of a sub n equals 0, then the series converges. All right, it does not make a statement about that. This test can only be used to prove that a series diverges, hence the name. If the limit as n approaches infinity of a sub n does not equal 0, then this test does not tell us anything. Is inconclusive, does not work, fails, is not helpful to us, etc. We must use another test. This test can be a great time saver. Always perform it first. All right, so example 5 says use the nth term test to determine whether the following series diverges. All right, and part A, we've got our series from 1 to infinity of 2n plus 3 over 3n minus 5. All right, it's not geometric. Let's use our nth series test. So we want to look at the limit as n approaches infinity of our rule there, 2n plus 3 over 3n minus 5. All right, so going back to limits, we're looking at limit going to infinity, so we can use n behavior model. Looking at our rates on the top, 2n, and on the bottom, 3n. And over n goes away, so we've got 2/3. All right, 2/3 does not equal 0. All right, so is this nth term test helpful there? Yes. So looking at our if-then statement, if the limit doesn't equal 0, that's what we got, then that tells us that our series diverges. All right, so therefore it diverges by the nth term test. All right, again, you always want to give what test you used and show your work for how that test helped you out. All right, part B, try that in your notes. Determine whether that series diverges or not, if it's helpful. Do the same thing for part C. We'll talk about those the next time we meet. And let's look at part D together. Okay, so our series from 2 to infinity of 1 over 1.1 in parentheses to the nth power, or to the n power. Okay, so let's look at this using our nth term test. So we want to look at the limit as n approaches infinity of our rule. All right, that denominator is a power function, or an exponential function, excuse me. So that bigger than 1, that means the denominator is growing to infinity. So that means that value is going to 0. All right, so our nth term test does not help. All right, we can say it is inconclusive. All right, we don't match up with that first half of that conditional statement of if our limit as n approaches infinity does not equal 0. So we can't use our nth term test here. So that means we want to try another test. All right, the only other test we've learned is our geometric series test. So can we rewrite this as a geometric? I think we can. All right, this is the same thing as series from 2 to infinity of 1 times 1 over 1.1 to the nth power. Okay, our R value is 1 over 1.1. 1 over 1.1. All right, so 1 over a bigger number is going to be less than 1. So what does that tell us? That tells us that it's going to converge. So it converges by GST. All right, we weren't asked to find what it converges to, so we'll leave it at that. All right, so there'll be times when we try a test, doesn't work, we'll try another test, all right, until we get a conclusion. All right, nice. Next up, our telescoping series. All right, a series such as 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, etc. Look for that pattern there. It's called a telescoping series because it collapses to one term or just a few terms. If a series collapses to a finite sum, then it converges by the telescoping series test. Excuse me. If it doesn't, then we can't use this test. All right, write out terms of the series until both the start and the ending terms cancel out. Then add the terms that do not cancel out to find the sum of the series. All right, so telescoping in the sense that it looks like it's really big, but it can be compressed into few. So if you notice in this test here, you can cross out those 0 pairs essentially. All right, we got Ed here showing us telescope. Thanks, buddy. All right, example 6 says determine whether the following series converges or diverges. If they converge, find their sum. Okay, so let's find the sum. We're just going to plug in values and look at the first at least 3 or 4, maybe more terms of this series and look for that pattern. Okay, so we're starting by plugging in this 1 here. So plugging in our 1, we get 1 over 2 times 1 is 2 plus 1 is 3 minus, and then plugging in a 1 in the second one. 2 times 1 is 2 plus 3 is 5. So we get 1/3 minus 1/5 is our first term. Let's go ahead and kind of block that off. All right, our second term, again, plugging in a 2. 1 over 2 times 2 is 4 plus 1 is 5. Minus 2 times 2 is 4 plus 3 is 7. And so on. Let's go ahead and find the next couple of terms. All right, we're going to get 1/7 minus 1/9. Plus 1/9 minus 1/11, and you get the idea. All right, and then we look and see, can we compress this? All right, so we've got a negative 1/5 and a positive 1/5. That's a 0 pair. Those go away. Negative 1/7, positive 1/7, 1/9, and so on. And you can kind of see as we go out for the rest of our series, every term after that is going to kind of undo itself with the next term. So all that we're going to have left is this 1/3 here at the beginning. All right, so we say our series converges to that sum of 1/3. All right, I'm going to let you do part B on your own. But wait until after we go over the next problem. So I want to do C together, and then I want you guys to go back and do B on your own. All right, so looking at example C, we've got the series from 1 to infinity of 1 over n squared plus 4n plus 3. Now, if we just went and listed out the first couple of terms of this one, well, we don't really have the two parts that we had in the last one that kind of gave us that zero pair kind of factor in there, where one was positive, one was negative, and as we saw, the second term in the second piece of the first term undid the first piece of the second term, and so on. And we don't have that here. So when we see that, we want to go back to our friend partial fractions. Because if you remember, with partial fractions, we do split up a fraction like this into two pieces and kind of see where it could have come from. So let's do that. So let's take just our rule here, our 1 over n squared plus 4n plus 3, and let's find its partial fractions. All right, so if we factor that denominator, then we can see where n plus 1 and n plus 3 are factors of n squared plus 4n plus 3. So then we can rewrite that as sum numerator a over the first factor plus sum numerator b over the second factor. All right, that's got to be equivalent. So we can take the that first numerator times our second factor in the denominator plus our second numerator times our first factor in the first denominator. And that's got to be equal to the numerator of our original, which is 1. Okay, so now we want to solve for a and b. So we're going to kind of handpick selected n values to make sure that we can solve each one. So for the first one, let's let n equals -3. All right, that's going to give us 0a, so that's going to essentially eliminate that variable. So for our b value, -3 plus 1 is -2. So we've got -2b equals 1. Solving for b, we get b equals -1/2. All right, let's see. If we solve this n plus 1, set it equal to 0, we get n equals -1. So let's plug in -1 into n in this first piece. We get 2a. Okay, this one, second piece is going to make 0. So we've got 2a equals 1. Solve for a. We get 1/2. So we can rewrite our sigma as the sum of two fractions. Okay, we've got our a value, which we found was 1/2. So I'm going to put that 1 in top, and I'm going to go ahead and put the 2 in the bottom. And for our b value, we got -1/2, so that makes this subtraction. I'm going to put the 1 in the top, 2 in the bottom, use that second piece, n plus 3. All right, again, just partial fractions so far, but now we've got a rule which is a difference. So now let's try our telescoping series test. And let's see, I'm going to come below that, see how much space I've got. All right, we're just going to plug in our values. Find our first term, plugging in 1. We get 1 over 4. All right, and our second piece, 2 times 4 is 8, so we get 1/8. All right, so that's our first term. Plugging in 2 to get our second term, we get 1/6, and so on. And for this one, I think it'll be valuable to go out maybe an extra term or two. All right, I think that's plenty. So now I think we can see the pattern from that. Let's see what we can cancel out. So I've got a negative 1/8 and nothing in the next term, but if we go to our third term, we've got a positive 1/8. Let's see, 1/6. I don't see anything that goes with that, but that negative 1/10, positive 1/10, that makes a zero pair. Negative 1/12, positive 1/12. And we can kind of see as we move forward from there, this negative 1/14 is going to cancel out with that that first piece of that sixth term, and so on. Each of those are going to cancel out from there on out. So we're left with this 1/4 and this 1/6. All right, and that's going to tell us what our series converges to. All right, so this is going to converge to our sum. All right, and our sum is 1/4 and 1/6. If we find common denominators, then that's going to give us 5/12. All right, so just a couple extra steps. Finding partial fractions for when you see a fraction with especially a quadratic or in part B. This is another good one to do partial fractions on again when you see that multiple factors in the bottom. Split them up into partial fractions, use the telescoping series, and see what it converges to. All right, two more tests to go for today. The next one up is called the integral test. And integral test says if f is decreasing, continuous, and positive for x values at least 1 and a sub n equals f of x, then we can say our sigma of a sub n and our integral from 1 to infinity of f of x with respect to x either both converge or both diverge. All right, first note, this does not mean that the series converges to the value of the integral. Second note says the function need only be decreasing for all x values greater than k for some k at least 1. Okay, so let's look at these examples together and see how this works out. All right, so notice that this doesn't give us a value for convergence. It just tells us whether we are going to converge or diverge. All right, example 7. Determine whether the following series converge or diverge. In part A, we've got the series from 1 to infinity of n over n squared plus 1. All right, let's see what we can do here. Okay, so if we try our nth term test first, then we can see that denominator is bigger. Plug in an infinity, that's going to approach 0. So our nth term test for divergence doesn't help us here because we do get 0. So let's try this integral test. So let's try to find our integral from 1 to infinity of our function n over n squared plus 1, in this case with respect to n. All right, so let's see, derivative of n squared is n. So if we do some u substitution using n squared plus 1, all right, solve for dn. All right, subbing in, we get our integral from 1 to infinity of n over u. And then dn is the same thing as 1 over 2n du. All right, we got an n in the top, n in the bottom. That gets rid of that n variable. So what are we left with? We've got this 1/2 here, so I'm going to pull that out front. We're still going from 1 to infinity, and we have 1 over u. with respect to u. Excuse me. That is a function that we can take the integral of. Okay, so 1/2 of, that's a natural log of the absolute value of u. Don't forget to sub back in what our u was, which was n squared plus 1. All right, and this is an improper integral, so we need to find the limit as b approaches infinity of our integral from 1 to b, all right, of all that, which we already found the integral of. So flash forward, we're looking to find the limit as b approaches infinity of what we found here, 1/2 of the natural log of the absolute value of n squared plus 1, and we're going from 1 to b. Okay, plugging those values in. All right, and then if we plug in infinity into our b, then we're going to see that we're going to get the natural log of infinity, which tends to infinity slowly, but it still goes to infinity. And this is just going to be 1/2 ln of 2, so that's still going to be infinity. So that tells us that this integral diverges to infinity. Oh, yeah. All right, so that means that by this integral test, because they both converge or they both diverge, in this case our integral diverge, so that means our series that we were given from 1 to infinity of n over n squared plus 1 also diverges. And then, of course, let's tell it what test we use. We use the integral test. All right, let's try one more of those. Okay, we've got the sum from 1 to infinity of 1 over n squared plus 1. All right, so again, let's try the nth term test. The denominator is going to grow to infinity, so that's going to approach 0. That doesn't help us, so let's try our integral test. So let's look at the integral from 1 to infinity of 1 over n squared plus 1 with respect to n. All right, again, an improper integral. It's going to be every time. So let's rewrite that as a limit. That is exactly our inverse tangent function. So let's go ahead and jump to that. We're going from 1 to b. Okay, so our limit as b approaches infinity of inverse tangent of b minus inverse tangent of 1. All right, I like to look at my tangent graph. Oops. Okay, on our tangent graph, we've got asymptotes. pi over 2 and negative pi over 2. We've got our function increasing, going through those 3 points from left to right. So if we're looking for the inverse tangent of b as b approaches infinity, so approaching infinity is up here. So that means our angle is approaching pi over 2. All right, as the inverse tangent of 1, or negative 1, excuse me. So negative 1 is this guy here. So we're looking at, no, that's negative 1. Positive 1 is this guy here. That's pi over 4. So pi over 2 minus pi over 4 equals pi over 4. All right, so that's a convergent integral. So since our integral converges, that means that our series also converges. Okay, last test for the day, P-series test. Okay, so a series of the form, the series from 1 to infinity of 1 over n to the p. So same P-series that you might recognize from when we did integrals of P-series. All right, it's called a P-series where p is a positive constant. If p equals 1, the series is called the harmonic series. We'll come back and talk about that more in the future. All right, if p is less than or equal to 1, the series will diverge. If p is greater than 1, the series will converge. Note, if the P-series converges and starts at n equals 1, we cannot find its sum using 1 over p minus 1 like we could with integrals. Okay, last 2 examples. So example 8 says, use the P-series test to determine whether the following series diverges in part A. All right, so we've got the series from 1 to infinity of 1 over n times root n. Well, that is not in that form, so let's see if we can rewrite it in that form. All right, so our sigma as n equals 1 to infinity, and that's the same thing as 1 over n to the 3/2 power. All right, so this is n to the 1. This is the same thing as n to the 1/2. Multiply them together means we add those exponents. All right, so this is P-series. We've got n to some power. Let's look at that power. That p-value is 3/2. 3/2 is greater than 1. So that means that our series converges by the P-series test. We can abbreviate that PST. All right, that's not so bad. Last one, part B. Another series from 1 to infinity, this time of root n over n. Again, we might need to, like in the last one, rewrite our rule so that it looks like a P-series test. So using your algebra skills to rewrite this as 1 over n to the 1/2. All right, we recognize this as P-series. Pick out that p-value. And 1/2 is less than or equal to 1. So that means that we are going to diverge. All right, so we have a collection of tests to determine whether certain series converge or diverge. We're going to add some more in our next lesson, and stay well.